Okay, this is Dr. Kraus with another Bode example. I want to do in this example a couple of things. So I want to talk about a pure double integrator and an S plus P1, I'm sorry, Z1, do two zeros, and an S plus Z2. So one, I'm just kind of randomly giving you one more example to work through. One, I've gotten some questions on email about, well, why doesn't it look like I expect it to look with two separate poles if the poles aren't far enough apart? So we're going to answer the opposite question that's related. So I'm going to have a gain. I'm going to have a Z1 and Z2. And so I want to talk about the gain. I want to talk about Z1 and Z2, especially as they get closer and closer together. And then I'll just throw in the S squared as a bonus. So I'm going to have this be my kind of F equals Z1 over 2 pi. And then I'll do another one over here. I'll call this F2. I guess I'll call this F1. Is equal to Z2 over 2 pi. So I'm going to have, as long as Z1 and Z2 are far enough apart, I'm going to come in, and so I'm going to initially be coming down at 40 dB per decade. That is my asymptote because of the double integrator. I expect that to happen. And then when I get to here, my slope will have plus 20 dB per decade added to it. So that'll take me to minus 20. And so I'm going to go along like so at now minus 20 dB per decade until I get to this point. And I'll take that negative 20 and add another 20 because of this zero. And so it will finally flatten out. And as long as my Z1 and Z2 are far enough apart, I'll see three distinct asymptote regions in my Bode plot. And my phase will start out at minus 180 because of the double integrator. We'll get to that first zero, and it will go up 90 degrees, like so, and it'll pass through 45 at that zero. And we'll get to the next one, it'll go up another 90 to 0. So I'm going to call this 0, I'm going to call this minus 90, this will be minus 45, this will be minus 135. And so I'll pass through those points, and my asymptotes will basically look like that little stair step. And then if I wanted to fill them in, they might look something like that. And similarly here, my asymptotes might look something like that, and my real Bode might look like something like that. Now, like I said, as long as Z1 and Z2 are far enough apart, we'll see these three distinct regions, and we'll see a double stair-steppy thing. But if Z1 and Z2 start to come closer and closer together, this region might not be as obvious. In a limiting case, if Z1 is equal to Z2, I would just see a 40 dB shift immediately in my slope, and my phase might look like I have a zeta equal to 1 second order 0. So we'll look at that on the Python plot in just a minute. The other thing I want to say about the gain, hopefully you remember from some of your basic kind of logarithmic properties that if I have the log of a times b, that's the same as log a plus log b. Well, that still holds true if I have 20 log 10 of a times b. That's the same as 20 log 10 of a plus 20 log 10 of b. So if I have a gain, so if I just have g times my other stuff, there'll be a dB value from this and a dB value from this, and the gain will just end up adding. So I'll have 20 log 10 of my gain plus 20 log 10 of my other stuff. So this is just a shift up or down in dB depending on my gain. So if my gain were 10, it would shift me up 20 dB. If my gain is 1, it shifts me nothing. If my gain were actually 0.1 or 1 over 10, it would shift me down a negative 20 dB per decade. Or sorry, not per decade, just 20 dB shifted all the way down. So this is just a vertical shift when I've got a multiplicative gain in my transfer function. Like so. So this multiplier just shifts the magnitude part up and down. So let's now do some Python examples. So I will have these things uploaded onto the internet. If I can type correctly. Sorry, 458, lectures, October 12th. So here is what I'll post is YouTube example 2. What I want you to see is I'm defining an F vector, an omega vector, and an S vector. And then I've just got Z1 and Z2. And for now, I've got a gain of 1, and Z1 and Z2 are fairly far apart. And I've got this transfer function, and I'm calculating the dB magnitude and the phase, and I'm plotting a Bode plot. And eventually, we'll wrap all of this. I already have code that would just kind of do this automatically, and I'll call it Bode utils, and I'll make it available to you guys. But we'll deal with that later. So, if I start my IPython SciPy thingy and run this, two things I want to talk about. So as you see this here, and let's make this a bit bigger. So right now, Z1 is 0.1 hertz and Z2 is 100 hertz. So you see that there's a line here and a line here, and if I let those intersect, they would intersect right about there. And then there's this line, and they would intersect right about here. And Z1 and Z2 are pretty far apart, so I see 3 distinct regions in my magnitude. And I see 2 like stair-steppy things of phase coming up 90 degrees. But if Z1 and Z2 were not as far apart, then it would start to be less obvious. So if I look at this phase, I still see 2 little inflections, and I still sort of see 3 regions of 3 different slopes on my dB mag. But as they start to come, whoops, there we go, closer and closer together, that becomes less and less obvious. And so now, even though they're technically a factor of 10 apart, it's hard to tell that in between 1 and 10 there's another region. And my phase, it's not obvious. Maybe if I zoomed in on the 10 to the 10 to the 0, 10 to the first region, I might see it. But it starts to look a lot like there's just a critically damped. And so especially if I have them actually equal to each other, this is in fact exactly the critically damped case. And so the only way to really tell would be to try to examine just how sharp is this corner. And now I should be 6 dB up from that corner because it's a 0, that's second order. So that picture versus, trying to see if I can show you this all at once. So before we had this factor of 10 difference. And so this was the Bode pot for kind of the critically damped 0. Now that, if I saved that, I didn't. Sorry, that's why I didn't change. Whoops. So that's a pretty, I mean, they've got to be a little bit further apart than that for you to really be able to tell it. So if you have the opposite scenario where there's maybe not a lot of spacing between 2 poles, it might start to look like there's just one critically damped or over-damped pole instead of 2 distinct first-order poles. And then again, as they start to grow further and further apart, it starts to become more obvious that there's something going on and there's 2 steps to this thing. And then the other thing I want to make sure I said, like I said, right now you can see this gain and it stops down here at like minus 70. If my gain were instead a 10 instead of a 1, the magnitude will shift up. And actually the way that Python's doing this, it's not obvious if you're not paying attention. The plot didn't change, but the y-axis changed. And so now we're ending at minus 50 instead of minus 70 where we were before. And if I make the gain even bigger, it will shift up again. And so now we're ending at minus 30. But again, like I said, you got to be paying attention. It's the y-axis limits that are changing, not the plot itself. Maybe it would be slightly more obvious if I made it not a clean factor of 10. It shifts a little. But still, the gain is doing nothing more than shifting the magnitude plot up and down. All right, I think that's all I got to say for this. Thanks.